Lecture 2, Organization of the Work. In this lecture, I discuss how the material is arranged into chapters, what sequence is followed, where a few things were placed, why we did things that way, and touch on a few highlights of particular sections. The various chapters in this book can be collected under 5 major topics. First, driven collective motion, including centrifugation and electrophoresis, treats experiments in which all of the molecules have roughly the same force on them. Second, under single particle motion, we have solvent motion, local segmental motion, dielectric relaxation, polymer self and tracer diffusion, and optical probe diffusion. By collective effects, we include the mutual diffusion coefficient, the relaxation of the dynamic structure factor, polymer viscosity, linear viscoelasticity, and nonlinear viscoelastic effects. The chapters also treat several special topics, notably quasi-elastic light scattering spectroscopy, which rates a methodology chapter of its own, and colloid dynamics. Finally, 3 chapters, conclusions, summarize the findings in the earlier chapters, point out some particularly outstanding results that are found as a result, and at the very end sketch a theoretical model that is actually consistent with what has been observed. Chapters 2 and 3 treat centrifugation and electrophoresis. Centrifugation is a very old technique for studying polymer dynamics. It goes back many decades. It can usefully be applied to study binary polymer-solvent systems, ternary polymer-polymer solvent systems, and probe systems, that is, probe polymer-solvent systems, all to give information on how polymers move under different conditions. The presence of a chapter on electrophoresis in a review and analysis of this sort is novel. There have been reviews that compared electrophoretic behavior with specific models for polymer dynamics, but here I advance the novel observation that electrophoresis, exactly like centrifugation, can be used to gain information not on the electrophoresing species, but on the polymer matrix through which electrophoretic motion is occurring. Chapters 5, 6, 7, 8, and 9 treat a variety of phenomena in which the motion of a single particle suffices to describe what is happening theoretically. We begin on the smallest scale with solvent dynamics, the motion of small and large particles through non-viscous and highly viscous solvents, showing that small objects in a simple solvent show non-Einsteinian, non-Stokes-Einsteinian diffusion and transport properties. We also discuss the fascinating recent result that just as the solvent modifies the dynamics of the polymer, so also do polymers modify the dynamics of nearby solvent molecules. We then advance to discuss local monomer dynamics as studied by fluorescence depolarization and other methods. We push ahead to treat dielectric relaxation, a remarkably flexible technique that gives chain radii, chain rotation times, and chain internal correlation rate times, and detailed relaxation spectra, all from one measurement. Stuck into the dielectric relaxation chapter is discussion of the observation that if you take a polymer chain, run up the local concentration of polymers in solution, the chain shrinks. That's usually referred to neutron scattering, but in fact there are 3 ways to measure that phenomenon. Dielectric relaxation turns out to be the most effective. We then push on to treat self and tracer diffusion, in which the motion of a single chain through the same type of chain or through different types of chains is measured as the single chain diffuses. And finally, we treat optical probe diffusion, the motion of spherical particles through a polymer solution. Optical probe diffusion has been studied for 40 years. More recently, the same systems under the cognomen microrheology have been studied. The optical probe diffusion studies are far more penetrating in what they show and in what assumptions you can actually safely make about these systems. Chapters 11, 12, 13, and 14 treat experiments in which the collective motion of polymer chains is important. By mutual diffusion, we mean the diffusion of material down a concentration gradient. As studied by dynamic light scattering, one obtains the dynamic structure factor, which tells how pairs of molecules move relative to each other in solution. Stuck into there is our one treatment of polyelectrolytes. In some neutral polymer solutions, the dynamic structure factor shows a slow mode, which appears to be very similar to the slow mode observed in polyelectrolytes, and which we show can be interpreted as Kivelson glass formation. We then treat viscosity, one of the most classical measurements, one of the original measurements showing that polymers are indeed macromolecules. We push ahead to linear viscoelasticity, the dynamic moduli, and shear thinning. In the chapter on linear viscoelasticity, we have to do something that was not done anywhere else. Namely, we have to change slightly exactly how we parameterize the measured phenomena in order to understand what's going on. Finally, the chapter on nonlinear viscoelasticity treats phenomena arising from normal stress differences, phenomena arising because polymer solutions have memory, and modern effects that are not otherwise treated, such as large angle oscillatory shear, non-quiescent shear relaxation, and similar effects. I put in a chapter on light scattering spectroscopy because it was the basis of my professional career. Also, there's a lot of wrong thinking in the published literature on the technique, and I set some of that straight. Why talk about colloid dynamics in a polymer book? Because colloids and polymers have the same colloid-colloid and polymer-polymer forces, hydrodynamics and volume exclusion. Only the shapes differ. Thus, compare colloids with polymers and you can tell what phenomena are in fact due to the shape of the polymer chains. The final three chapters bring together what has been seen earlier. There is essentially nothing new in Chapter 15, the qualitative summary. I list very qualitatively high points of each of the earlier chapters so that readers who found a chapter tedious may discover what they missed and be motivated to go back and look again. Chapter 16 summarizes major results. In particular, experiment is overwhelmingly adequate to disprove any belief in scaling-type descriptions of the concentration and molecular weight of polymer dynamic parameters. Furthermore, there is a traditional notion that if we have a diffusion coefficient, we can write it as being inversely proportional to so-called dynamic scaling length, psi. That's entirely appropriate in critical phenomena where psi shows some sort of a correlation length. As is conclusively shown by the treatment of colloid dynamics, for the treatment of macromolecule diffusion, interpreting D in terms of psi is totally wrong and gives results that are the opposite of what is actually occurring. Finally, it turns out that experiment and modern theory are totally adequate to conclusively disprove, refute any belief in the notion that there is hydrodynamic screening in polymer solutions. There are more results in that chapter. I'm not giving all of them. The closing section, the afterword, very briefly sketches a theoretical model that is consistent as far as it goes with everything that has been said so far. Future lectures will treat chapter by chapter the contents of the book in greater detail.